Welcome to my video on the position vector for circular motion. This is a continuation of my series on circular motion, the physics tutorial. I'll put a link to the previous video at the back of this one. What we want to look at is we want to look at the position vector for a particle, and this particle is in circular motion. And it's going to be on the XY plane. So that's what we're looking at. So let's draw a picture of that. Here's our circle that the particle is moving in. There's our particle P, and it's just rotating around the circle. So let's start understanding this with a little math to it. Here's our center of the circle. This is our x-axis. It changes with time, meaning the point is moving. Y of t. Now if we draw our position vector out here, r of t, that's the position vector out to that point. And then there's our theta of t, our angle changing with time. Now if we look at this distance right here, this is going to be our y of t, but it's in the j of direction. It's along the j unit vector. And correspondingly, this distance right here is x of t, but it's in the I unit vector direction. It's along the x-axis. So that kind of labels all the points. Now that we know x of t is equal to r cosine theta of t from the definition of the cosine, and then y of t is equal to r sine theta of t. So there's our basic relationships between the x and y relative to r and then the angle. Now we do know that r of t, the vector, is going to be just x of t, I direction, plus y of t along the j unit vector. Now putting in these values into that, basically we're putting this relationship, these two relationships, into that equation right there. So we're going to get r cosine theta of t times I plus r sine theta of t, and then that's going to be in the j direction. Now let's go calculate the magnitude of r of t. I'm going to go to the next page to do that. Now we know the magnitude of r of t is just going to be equal to, when we take the magnitude of the vector, we square the components, take the square root. So that's r cosine theta of t, quantity squared, plus r sine theta of t, quantity squared. Take the whole thing to the square root power. Now we can factor out an r, actually an r squared, that's going to be equal to the cosine squared theta of t plus sine squared theta of t. We just factored that out, factored the r squared out, and that's equal to 1/2. Well, the whole quantity, we take the square root of it. But now we realize that this right here is just equal to 1, because the cosine squared of an angle plus the sine squared of an angle is equal to 1. That's a trigonometric relationship. So now if we go back and substitute that in, the magnitude of r is equal to the square root of r squared times 1, which is just equal to r. So there's our relationship. And that just tells us that makes sense. The object is moving around this circle at a constant distance r from the point of origin. So what we can say is the magnitude of the motion, vector r of t is the fixed radius r, so it's going to be the radius r, and does not depend on time. In other words, it's a constant distance away, but the angular coordinate, that'd be theta of t, is time dependent. So that's what we can say. It's just either a constant distance and the angle is constantly changing. Well, I hope you got something out of this video and learned a little bit about the position vector and how you break it down trigonometrically. And thank you for watching.